Okay, in this video we're going to start the 2.6 notes. So in these notes, the first section is on inventory control problems. So they are very new problems for you. So we're going to have to go over some background knowledge. So first off, what you need to know is that when you do an inventory control problem, there's an underlying assumption that your constraint is always going to be Q equals R times X. They're not going to tell you that. That is the underlying constraint. So Q is the quantity you order of, or the quantity you sell of something in an entire year. R is the number of orders you place in a year. And X is the number of units in your order. So here is your constraint. Okay, so when you do inventory control problems, you need to remember that you have to know this. So other things you have to know is that an inventory control problem is a cost minimization problem. So what you're going to do is you're going to minimize the costs associated with maintaining an inventory. Okay? Minimize the costs associated with maintaining an inventory. And there are two such costs. One of the costs is the carrying cost. So under the carrying cost, you could have such things as storage costs. So right here it's going to be storage costs. It may be insurance. Okay, it may be the cost of capital tied up in an inventory. Those are carrying costs. Then in addition, you have ordering costs. And ordering costs is basically the cost of placing an order. So you may have some freight charges. You may need clerical help to place the order, clerical help to check in the order and to move it to the place it's going to be stored. So those are the kind of things under ordering costs. Okay, the most important thing you need to know about this, in addition to this being the constraint, is that your carrying costs fall under two categories. They can be based on the average inventory. So for example, if you order 100 units every month, then you order 100, you sell off, you get to 0. If you are calculating your carrying costs based on your average inventory, then you take whatever was in your order and divide by 2. If instead you are calculating your inventory or carrying costs based on the total inventory, you multiply by what you ordered, the X. So that's going to come into play as we explain the first problem. So the first problem deals with orange juice inventory. So it says, suppose the store manager wants to optimize. So in this case, optimize does not mean maximize. Okay, optimize means the best case scenario for the problem. If a store manager wants to optimize his inventory costs, he wants to minimize the cost. That is the best case scenario for him. So this is a minimization problem. Okay, the manager plans to place several orders of the same size spaced equally throughout the year. You will always see this wording, same size, spaced equally throughout the year. That means that you don't have what they call a dynamic programming type problem where the order sizes are changing and the spacing is changing. This is going to be a constant scenario. So it's going to minimize the complication of our problem. Okay, use the following data to determine the economic order quantity. So that means what's the best scenario for ordering, what size order do I want, and how often should I place it. So that is an economic order quantity. Okay, so here's the data. 1,200 cases of orange juice will be sold over the year. That is your Q. Okay, we know that Q equals Rx. So right now we know that 1200 equals Rx. What does R equal? R equals the number of orders, and X equals the number of units in each order. Okay, our ordering cost for each delivery is $75. Okay, ordering costs will be the small r. So wherever you see ordering costs, I want you to put a small r, and it's going to be $75 times the number of times we place that order. Okay, the carrying cost. Okay, carrying cost is going to be based on your X, and the X is the number of units in each order. Carrying cost is $8 for 1 case of orange juice in inventory for 1 year, based on the average inventory. So, $8 times the total order, but now it's based on the average inventory, so take your total order and divide it by 2. Okay, that's an important detail. Alright, so now we're going to figure out what our economic order quantity is. So what we're going to do is we're going to use our constraint, just like we always do, and let's sub out for R. So take your constraint, divide both sides by X, and now I know that R is 1200 over X. So what are our costs? Well, our costs equal 75 R plus 8X over 2. Okay, so let me just change one thing. I said R, but I wrote C. So this is R. Okay, R is equal to 1200 over X. So I'm going to write this again. C equals 75 times 1200 over X plus, let's reduce 8X over 2 to 4X. Okay, one more time. C prime equals 75 times 1200 is 90,000. Bring your X up. It's to the negative 1 power plus 4X. Okay, we're going to take this derivative and solve this on the next page. Okay, to continue, so I have my, I don't have a first derivative, but yes I do. I have my first derivative, no I don't, set up. I have my function set up to take a first derivative. Now let's take the first derivative. So it's C prime equals negative 90,000 X to the negative 2 plus 4. Now while I'm at it, let's go ahead and take the second derivative. The second derivative equals positive 180,000 X to the negative 3. Now what do we know about this second derivative? Well, since X has to be a positive number, that's the number of units in my order, it cannot be negative, C prime prime has to always be a positive. If it's always a positive, then I know my second derivative test tells me that my second derivative reveals concave up, which is a min, which is what I want. So now that I know I'm on the right path, let's go ahead and set our first derivative equal to 0, and we'll solve for our X. So setting it equal to 0, I get 90,000. Bring your X, negative 2, down to the bottom as X squared. That's going to equal 4. View this as fraction equal to fraction and do your cross products. So 4x squared equals 90,000. Divide both sides by 4, and you get x squared equals 22500. X has to be positive or negative 150, but since it has to be a quantity we're ordering, it's going to be positive 150. Okay, so now we have to remember that Q equals R times X, and we already know that Q has to be 1200, so we had already set up that R equaled 1200 over X, and if X is 150, then doing the math, we can see that R is going to equal 8. This is our economic order quantity. So we have found that we should place 8 orders of frozen orange juice cases, and in each order we should have 150 cases. Okay, that will get us our quantity sold in a year of 1200. Alright, so that's how this problem goes. We're going to now work on the next page, and in that page we're going to just see if we can analyze the setup and answer some questions. Okay, take a second to look at this figure 8. Figure 8 shows us some inventory, which is labeled on the y-axis right there, and then I see the number goes from 0 to 180. I see right here the first order arrives, and here is the end of the year. So now let's look at the information presented in this problem. It says inventory problem. Figure 8 shows the inventory levels of dried Rainier cherries at a natural food store in Seattle, and the reorder periods over 1 year. Refer to the figure to answer the following questions. Okay, so you have the idea of what's going on here. Question A says, what is the average amount of cherries in inventory during one reorder period? So one reorder period is one blue line. So during that period, they ordered 180 pounds and they sold them all. So the average of 180 plus 0, so 180 plus 0 divided by 2 gives me 90. So the average inventory during that one reorder period was 90 pounds. Question B says, what is the maximum amount of cherries in inventory during one reorder period? So what's the maximum? The maximum will be 180 pounds. What's the minimum? The minimum would be 0 pounds. How many orders were placed during the year? Every blue line represents an order. They order 180, it comes in, and then it leaves when all the 180 pounds is being sold. And then they order again, again, and again. So there are 1, 2, 3, 4, 5, 6 order times during 1 year. How many pounds of dried cherries were sold during 1 year? Well, we ordered 6 times. Each time was 180 pounds, and everything sold out. So 6 times 180 gives me how much was ordered for the entire year and successfully sold. And that's going to be 1,080 pounds of cherries. So make sure you understand that. Make sure you can read this chart. On the next page, we're going to talk about something with this problem, and we're going to assume that the economic order quantity, so the economic order quantity is exactly what we see here, which is that R is going to be 6 and X is going to be 180. So given that, what will we do in terms of our costs? That's the problem on the next page. Alright, up in the corner here I put our economic order quantity that was identified from the table on the previous page. So this is EOQ, if you want to abbreviate it, economic order quantity. So this says, now refer to figure 8. So I've done that, and I gave the appropriate information right here. Suppose that the ordering cost for each delivery of dried cherries is $50. So that's going to mean that the ordering cost is the R. So I know that if the R, well, let's say that it's 50 times R is the general expression for my ordering cost, given the cost of $50. And then secondarily it says, it costs $7 to carry 1 pound of dried cherries in inventory for 1 year. So that would be 7 times X, the number of dried cherries in an order. Part A says, what is the inventory cost for this problem if carrying costs are computed on an average inventory? So that means that you're going to take your inventory right here for your X and divide it by 2. So to do problem A, we're going to say that costs equal 50 times R plus 7 over X, but that X is going to be the average X, so I'm going to divide by 2. Okay, for A, I already know the costs because I have established by the table on the previous problem that the R is 6 and that the X is 180. So if you do the math, what you will find is that your cost is going to be $300. This is 300 plus 90 times 7, which is another 630. So your total inventory cost for the cherries would be $930. Okay, then on the next page, we're going to figure out, all right, if we have instead an inventory cost, and maybe we'll do it right here. So here is A. Let's see if we can figure out what B would be. And how does B change what I have for A? B says, what is the inventory cost if carrying costs are computed on the maximum inventory? So, changing to red, what changes? Right here changes. Instead of computing it on the average, which I get by dividing by 2, I don't divide by 2. So let's see if I can kind of put B maybe up here. So I'm going to start B here. So for B, it's still going to be 50 times R, that has not changed, plus 7 times plain old X, because I'm computing my inventory costs based on the maximum inventory and not the average. So that carrying cost component is based on the maximum inventory. Once again, I still know that my R is 6 and my X is 180. So doing that math, I'm still going to get an ordering total cost of $300, but my inventory cost that's composed of the carrying cost is greater. Now it's going to be 7 times 180, not 7 times 180 divided by 2. So 7 times 180 is 1260. So now in case B, I have an inventory cost of $15.60. So you see that this price has gone up significantly from the $9.30, and the change happens because of what I have circled in red. Average inventory calculations are cheaper than maximum inventory calculations. That is your economic order quantity discussion. So now what you can do is we're going to go back and look, and the homework that's on inventory control is right here in the textbook. I want you to do 3 problems. I'm going to go on and teach the rest of this packet right now on the following pages. Okay, in this problem, we're going to go back to problems that are similar to what we covered in 2.5. which was just straight up optimization. So we're going to read the problem and identify a constraint and an objective function. Okay, so let's go ahead and we'll read the problem. So it says, a rancher has 204 meters of fencing from which to build 2 corrals. One corral is square and the other rectangle with length that is twice the width. Find the dimensions that result in the greatest combined area. So I can readily see that the constraint is that my perimeter, which is the fencing, has to add up to 204 meters. So I see I have 2 variables. So let's figure out what the equation will be for this constraint. So I'm going to go ahead and I'm going to fill in another h here and an h here and an x here and a 2x here. So now what I know is that my constraint is that 204, and it's going to be meters. Let me just that up. 204 has to equal, so 2x, because x plus x, so that's 2x, plus 2x plus 2x is 4x, and then plus I have h plus h plus h plus h, so that's 4h. So let's simplify this a little bit. So 204 has to equal, combine like terms, I have 6x plus 4h. And all the red right here, this red, will be the constraint. Okay, so this is my constraint. I'm going to use that to get rid of one of my variables, which I know is going to show up. So it says find the dimension that results in the greatest combined areas. Okay, so let's switch over to a different color. And our area, which is going to be our objective function, is going to be length times width of the rectangle, so 2x times x is 2x squared, plus the length times width of the square, which is h times h, which is h squared. So we need to replace either an h or an x. Since we're multiplying by 2 for the x, I think I'm going to replace the h. So let's go back to our constraint. So we'll work with that some more. And our constraint tells us that if I want to replace the h, 204 minus 6x over 4 will equal h. So what should I do with that? Well, 4 will go into 204 51 times minus, let's reduce this to 3 halves x, and that's what h is going to equal. So that's my constraint written in h in terms of x. So now what we'll do is we'll play around with the colors a little bit. So area is going to be 2x squared plus, and I'm going to take my constraint now for my h, but it's going to be 51 minus 3 halves h, and I have to square it. Okay, so let's think about this. Do I really have to square it? And the answer is no, because I know the chain rule. So let's go ahead and without squaring that, which just makes for more math and more potential mistakes, let's take the first derivative because our job is to maximize the area. So a prime equals, okay, 4x, that was easy. Okay, now we're going to use the chain rule. The chain rule is going to get me 2 times whatever was in the parentheses, and then times the derivative of the parenthesis. So this derivative is negative 3 halves. So that was not bad at all, was it? So now at this point, I'm going to do a little multiplication, but it's going to be a lot easier to handle. So what do I end up with? So let's see. A prime is going to be, I still have the 4x, So I have 2 times 51, but then it's also times a negative 3 halves. So that's going to be a negative. The 2's will cancel. And what is 3 times 51? Well, that's 153. And do I have an x attached there? Let me think about that for a second. I don't believe I do. So I think I just have 153. So that part's done. Now let's go for the next piece. So I have 2 times negative 3 halves, but then that's being multiplied by another negative 3 halves. So that's going to be plus 3 halves times 3 halves is going to be 9/4 x, but then I have a 2, so that's going to be 9/2 x. So try to do this on your own and see if that works out for you. Alright, let's see if we can start combining some terms. So I have 4x, but then I have 9/2. So what I could do is make 4x 8/2. So let's do that. So my 4x, I'm going to instead make 8/2. So now my a prime is going to be 8/2 plus a 9/2x, so that's 17/2x minus 153. Okay, that is my first derivative. What is my second derivative? That's going to be a prime prime, and that will be 17/2, which no matter what I do will always be a positive number, and therefore if it's a positive number, I am going to, it looks like I'm going to minimize my function by finding this critical value. So that's kind of interesting, isn't it? Because I'm trying to find the greatest combined area. So let's be on the lookout for this, because this could become kind of interesting. Okay, let's keep proceeding, and then we'll figure out what we're going to be doing. All right, so let's just say we're going to continue down this road. So if I continue down this road, what I would do is I would solve for my a prime equals 0. So let's do that on the next page. Okay, so we're going to continue doing this just because I want to do some more investigating. So our normal procedure would be to set your a prime equal to 0. So let's do that. And if we do that, we say 17/2x equals 153. So x equals 153 times, just flip over the other thing, times 2/17. And we're going to end up with x equals 18. Using our constraint, we're going to get h equals 24. Now, if you didn't check your second derivative, you would think that you have found the measurements that would maximize the area. So what have we found? So let's do our two drawings. Our rectangle, if this is the case, would be 18 by 2x, so that's 36, and our square would be 24 by 24. Alright, so let's check what the area would be there. Okay, so I've done some calculating here. Using the measurements we just got when we did this optimization, we would have a rectangle of 18 by 36, which would give us an area of the rectangle of 648 meters square, and we would have a square of 24 by 24 meters, which would give us an area of 576 meters squared. If you add them together, I'm going to have an area of 1,224 meters square. Okay, that kind of sounds like a lot of of area for any kind of rancher. Okay, but I have a nagging problem. I know that my second derivative is indicating to me that I have found the least amount of area. Was that what I wanted to do? Of course not. So go back and look at your original function for area. So I'm going to write it up here because I went back and looked at it myself. So what I have is that my area equaled 17 over 4 x squared minus 153x plus 2601. So why was I so surprised that I did not get a maximum? I can see right away that I should have noticed that my leading coefficient was positive, and therefore I have an upward facing parabola. So this should not come as any surprise to me. So let's see what I have here. So I'm going to graph this parabola. So where should we graph it? So let's see what we have. Why don't, since I'm dealing with my x and I'm using that to get my best answer, what I'm seeing is I know that if my x is 0, my y-intercept, which would be right here, is going to be 2601. So this is an endpoint solution right here. If my x is 0, then I have a y-intercept of 2601. So that means that if I set x to 0, and x is in my rectangle, because remember the rectangle was 2x by x, so that would mean that I wouldn't have a rectangle, that I would use all my fencing to build my square and not my rectangle. That would give me an area of 2601 if I used all my fencing in that way. All right, what area did I find? I found 12, 12, 2, 4. That happened when x was right here at 18. So that means that and we'll just put it here, it's not really to scale, but this is 1, 2, 2, 4. That gives me my minimum of my function. So I have this point here, I have this point here. What if I used all my fencing and I used it on the rectangular piece? What would that mean? Well, if my h was 0, then therefore all my fencing, so 2x plus 2x plus x plus x, so basically 2, 4, 5, 6x would equal 204. So therefore, if I said that, so 204 divided by 6 gives me 34. So if I instead used everything for the rectangle and I have my x set at 34, what does that give me? That's the other extreme. That's the other endpoint. And that is my answer. If I used everything here, what would my area be? Well, if I know that 6x has to equal 34, so therefore 34 divided by 6 is going to give me 5 2/3. So I'm going to use my x will be 5 2/3 here, and then my 2x will be 10 4/3, which is 11 1/3. Okay, so if I multiply those together, I'm going to get an area. If x is 34, my area will be 2312, and that is great. All right, for our last problem in this section, it's a volume problem. So it says an open rectangular box. So open is a key word here, open. Rectangular box is to be constructed by cutting square corners out of a 16 by 16 inch piece of cardboard and folding up the flaps. So you see what you're doing? You are cutting square corners, so that's important as well. So find the value of x for which the volume of the box will be as large as possible. So your volume of your box, volume is always length times width times height. So in this situation, it's going to be w squared, w times x. So it's going to be w squared times x. And we want to maximize this volume, so that means that this is our objective function. Okay, our constraint is how big a piece of paper we have. So this is a very nice diagram. I need to figure out what kind of measurements I have here, so let's think about this. I know my volume is going to be length times width times height, and then I have some information here about what I'm looking at. So instead of really having an objective function and a constraint, I am going to build my constraint by identifying, I'm going to alter my objective function, I should say, by identifying some of the missing values that I have. Right now I have two variables. Can I get that down to being one variable? And the answer is yes, if I look at this carefully. So I know that my paper is 16 by 16 initially. But when I cut out those squares, what will each square side be? Well, each little piece right here is going to be x. So my dimensions for my w is really 16 minus 2x. That equals my w. Okay, and then what about the other w, which is the same, the measurements, right? Because over here, knowing it's going to be a square, I know that everywhere my length will be 16 minus 2x. So now let's see if we can write our objective function in only one variable. So I have v equals w squared times x. Well, my w will be 16 minus 2x. So now I know that v equals 16 minus 2x squared. And then I'm going to multiply that by x. Okay, so since we don't know how to do the product formula yet, I'm going to have to FOIL this out. So my volume is going to equal 16 minus 2x times another 16 minus 2x, and I'm going to just throw the x in front here. So let's go ahead and do that math. So volume equals x, and if I FOIL these two factors, I end up getting, let's see, 256 times x, excuse me, let me backtrack that, 256, and then minus 64x squared, or 64x. Okay, let me backtrack a little bit here so I can write a little neater. Okay, let me just write the whole thing out. If you FOIL this and multiply by the x, you end up with the following. So I get negative 64x squared, and I get a positive 4x cubed, and I get a positive 256x. Okay, that is my volume equation. Now what I'm going to do is take the first derivative. So v prime equals, so I have 256 minus 128x plus 12x squared when I wrote it all out. Alright, so now I know I have a cubic initially, and now I have a quadratic that's very difficult to really factor. So you can use quadratic formula. You can divide through by 4 first. The bottom line is, if you do factor it, I end up with 4 times x minus 8, and then times 3x minus 8. So I have 2 roots. So what I find is the 2 roots give me 2 critical values. So I'm going to test one critical value, which in order on the number line is going to be 8/3. I get that from my second factor right here. My other critical value is going to be 8. When I plug in and check my first derivative test, what I'm going to find is that to the left of 8/3 I'll have a positive slope, then I'll have a negative slope, then I'll have a positive slope to the right of 8. So what's going to happen is I initially will get a max for my volume, then I'll have a min if I use 8 for my critical value. Think about this. If you cut out a box that's 8 by 8, then W, which is 16, is going to be W 16 minus 8 minus 8. You'll have 0 width. So you are going to get a minimum, which is what my arrows are indicating. So when I do a second derivative test, what I find is my second derivative equals 24x minus 128, and that tells me when I plug in 8/3, I will get a negative. A negative for a second derivative test tells me I have a max for the volume. If I plug in an 8, I'll get a positive second derivative. That tells me I have a min. So what I have found is that in order for my volume to be maximized, I have to have an x of 8/3. So that's my final answer. There's a lot of math involved here. You don't always get nice, neat answers, but it's important to evaluate to see whether you are getting a max or a min. So to get a max, I need to cut flaps that are from the corners of 8/3 of an inch. Okay, so that's the last problem. You can now do every problem in this section, which is 2.6.